Okay, we're going to start 12.4, which is on the cross product. So last time we saw the dot product, right? Which was if we had two vectors a and b, if we took the dot, this was a1, b1 plus a2, b2 plus a3, b3. So this, you started with two vectors, and you outputted a scalar, a number, right? And that scalar told us about orthogonality. This told us about if when two vectors are perpendicular, the dot product is 0. But now we want to find a way, so our goal is to find a way to start with two vectors and output also a vector, and output a vector. And that's hopefully in some way geometrically meaningful. And the way we're going to do that is by the cross product. So given, say, A, which is A1, B1, A1, A2, A3, and B, which is B1, B2, B3, we define A cross B. So this is the cross product as the following. Okay, it's going to be the determinant of the following matrix, I, J, K. Here are vector quantities, and then there's A1, A2, A3 corresponding to the first term, A, and then B1, B2, B3. And for short, just like we talked about in the last video, we're simply going to write this with straight lines here, I, J, and K, A1, A2, A3, and then B1, B2, B3. So how does this actually come out? Well, let's expand about the first row. So we have I times the determinant of the minor matrix, A2, A3, B2, B3. And remember, you get that by crossing out the corresponding column, crossing the corresponding row, and then taking what's left over. And then we expanded by the next term, minus j times the determinant of its minor, which we'll see is going to be A1, A3, B1, B3. So if you cross here and cross here, you're left with A1, A3, B1, B3. And then plus K. Remember that we alternate signs here. There's a positive I, a negative J, and then the positive K times the determinant of its minor matrix, which is cross out the column, cross out the row, and you're left with A1, A2, B1, B2, and just erase these underlines. So what is that? Well, this is A2, B3 minus A3, B2 in the first coordinate, and then minus j times A1, B3 minus A3, B1 plus, I guess just for consistency, let me put the j on this side. So this is j, and then plus A1, B2 minus A2, B1 times k. So in coordinates then, if you multiply this out without the writing the ijk, this is A2, B3 minus a3b2, comma, there's a negative sign here, so I have a3b1 minus a1b3, comma, a1b2 minus a2b1. And this is called this vector. So this vector here, which is A cross B, is the cross product of A and B. So you say, okay, well, that seems kind of like a lot, and does that have some meaning? And it does. It's actually, there's kind of a nice way to think about it. So let's call this a little theorem, which we'll prove in just a second. We'll first do an example and then maybe prove at least some part of it. So A cross B is orthogonal to A and to B. Okay? i.e., so in particular, if you take the vector A and you dot it with A cross B, this equals 0, and the same with the vector B. If you dot it with this, you'll get 0. Well, I guess since we're here, before we do the example, let's just show one part of this. Let's show that this is true, and I'll leave you to think about the other part. So let's take A1, A2, A3, and dot it with this giant cross product here. So it's going to be just an exercise in symbolic notation, but it is a sufficient proof to show that this is actually orthogonal to the cross product. So what is this equal to? Well, what do we have? We have A1, A2, B3 minus A1, A3, B2. That's the dot product for the first term, plus A2, A3, B1 minus A1, A2, B3. That's the second term. And then the third term is plus A3, A1, B2 minus A3, A3, A2, B1, right? And so, for example, the A1, let's do this with some colors, A1, A2, B3 minus A1, A2, B3, those go away. Minus A1, A3, B2 plus A1, A3, B2, those go away. And let me just use the original color here. Plus A2, A3, B1 minus A3, A2, B1, same permutation of the same thing. Those cancel, and that gives you 0. And similarly with the B ones, similarly B dot A cross B. I'll let you guys think about how to do that. Oops, not 0 vector, but just a 0 number. Okay, so let's just do one example, and we'll end with that. So let's say A is 1, 2, negative. Oops, sorry. Let's make a simpler example. 1, 0, 0, where we can actually see what's happening. B is 1, 1, 0. So what does this look like? Well, here's 1, 0, 0 pointing in the x direction. Well, let me first draw my coordinate plane. So let's say we have, here's our x, y, z coordinate system. And here is the vector 1, 0, 0. This is A. B is 1, 1, 0. So it's sitting right here in the xy plane. So this vector is B. It makes sense that the the third vector, the cross product, which I'll denote with a green arrow here, it should be somewhere along the positive or the negative z axis, because you can see visually that this vector here, or any multiple of this, so A cross B should lie along the z-axis. Okay, because that, you can see visually that that'll form a 90-degree angle with the B vector. It'll also form a 90-degree angle with the A vector. So let's check that that's actually what we see visually there is actually what happens. So A cross B, well, what is that? You first put your I, J, K, then you put your A vector first, then you put your B vector. Well, what do we get here? Let's just expand. So we have I times the minor matrix, cross out the row, cross out the column, we get 0, 0, 1, 0, minus J times the determinant of the minor 1, 0, 1, 0. Again, you cross out the corresponding row, cross out the column, what's remaining, and then plus K times 1, 0, 1, 1. And you can see here that if you'll get 0, because 0 minus 1, so you get 0i minus 0 minus 0, so 0j, plus here you get 1 minus 0, you get 1k. So this actually is the vector 0, 0, 1, which lies along the z-axis. Okay. Okay, so this is, I wanted to give a simple one which we could actually visualize. And what I'll do is I'll leave you guys with an exercise here to try. And you can just do this algebraically. So let's let A be 1, 2, minus 1, and B be negative 2, 0, and 3. So compute A cross B. And go ahead and show then that A dot A cross B is equal to 0, and B dot A cross B is equal to 0. Okay, we'll end with that, and next time we'll do some more properties of the cross product.